Hello, today we will learn about Unit 5, Physical States of Matter. After completing this unit, you will be able to understand the kinetic molecular theory and properties of the three physical states of matter, know the behavior of gases by using the variables volume, temperature, pressure, and number of moles, know the terms like ideal gas, diffusion, evaporation, boiling, condensation, vapor pressure, boiling point, molar heat of vaporation, molar heat of condensation, melting, fusion, sublimation, melting point, freezing point, molar heat of fusion, and molar heat of solidification. Understand gas laws. Develop skills in solving problems to which the gas laws apply. Perform activities to illustrate gas laws. Carry out experiments to determine the boiling points of liquids and the melting point of solids. Demonstrate an experiment to show phase changes, and demonstrate scientific inquiry skills such as observing, predicting, comparing and contrasting, measuring, interpreting data, drawing conclusions, applying concepts, and making generalizations. The contents of this unit are Subunit 1, Introduction. Subunit 2, the kinetic theory and properties of matter. Subunit 3, the gaseous state. Subunit 4, the liquid state. Subunit 5, the solid state. Subunit 1, Introduction. The physical states of matter are solids, liquids, gases, and plasma. Solids have a definite shape and volume. They are extremely difficult to compress. They have higher densities than gases and liquids. The particles are rigidly held in a fixed position. They are not fluids. You can see in this picture the way that atoms are arranged in a solid. Liquids have definite volume but not definite shape. This is how liquids atoms are arranged in a liquid. They are slightly compressible. They have lower density than solids but higher density than gases. Particles are less orderly arranged than solids. They flow much more slowly than gases. They are fluids. Gases have no definite shape and volume. This is how atoms are arranged in gases. They can be easily compressed. They have lower densities than liquids or solids. Particles are in an irregular pattern. They exert pressure in every direction, and flow and diffusion happens throughout a given space. They are fluids. They can flow throughout a given space. Plasma is the fourth state of matter, and it exists at high temperatures. It is a gaseous mixture of positive ions and electrons. Extreme temperatures are needed for fusion, for example. In summary, matter is anything that has mass and occupies space. Matter exists in the form of a solid, liquid, gas, or plasma. Solids have a definite volume and a definite shape. A liquid has no definite shape, it takes the shape of its container. Can oxygen exist as a liquid and a solid? Oxygen can exist as a liquid and a solid at very low temperatures and/or high pressures. What is dry ice? Dry ice is solid carbon dioxide. Compare and contrast the three states of matter. Some properties are shape, volume, compressibility, and motion. Solids have a fixed shape. Liquids take the shape of their container. Gases don't have a definite shape. Solids have a fixed volume. Liquids have a fixed volume. Gases do not have a fixed volume. Solids are not compressible. Liquids are very difficult to compress, but they are slightly compressible. And gases are very easy to compress. Solids have a restricted motion. Liquids slide over each other. Gases move everywhere. Subunit 2, Kinetic Theory and Properties of Matter. By the end of this section, you will be able to give examples for each of the three physical states of matter. State kinetic theory of matter. Explain the properties of the three physical states of matter in terms of kinetic energy. And compare and contrast the three physical states of matter. The kinetic theory of matter gives an explanation of the nature of the motion and heat energy. According to kinetic theory of matter, ions, atoms, and molecules found in every substance are in a state of continuous and random motion. It is based on these assumptions. All matter is composed of particles which are in constant motion. The particles show kinetic and potential energy. The difference between the states of matter is due to their energy contents and the motion of the particles. Gases have no definite shape or definite volume. They can be easily compressed. They have low densities compared with liquids and solids. They exert pressure in all directions, and they can easily flow and diffuse through one another. Liquids have definite volume but no definite shape. They have higher density than gases, and they are slightly compressible. Liquids are fluid. Solids have definite shape and definite volume. Solids generally have higher densities than gases and liquids. Solids are extremely difficult to compress, and they are not fluids. In gases, particles are much more widely spaced and move much faster than in liquids or solids. Some solids directly change to gases by the process of sublimation. Arrange the three states of matter in increasing order. Intermolecular force. Gas is less than liquid is less than solid. Density. Gas is less than liquid is less than solid. Compressibility. Solid is less than liquid is less than gas. Kinetic energy. Solid is less than liquid is less than gas. Subunit 3, the gaseous state. By the end of this section, you will be able to explain the assumptions of kinetic molecular theory of gases. Describe the properties of gases using kinetic molecular theory. Describe the behavior of gases by using the variables volume, temperature, pressure, and number of moles. State Boyle's law. Perform an activity to show changes in volume and pressure of gases to illustrate Boyle's law. Apply Boyle's law in solving problems. State Charles's law. Perform an activity to show changes in volume and temperature of gases to illustrate Charles's law. Apply Charles's law in solving problems. Derive combined gas law equations from Boyle's law and Charles's law. Use the combined gas law to calculate changes in volume, pressure, or temperature. Define an ideal gas. Derive an ideal gas equation from Boyle's law, Charles's law, and Avogadro's law. Compare the nature of real gases with ideal gases. Solve problems related to ideal gas equations. Define diffusion. State Graham's law of diffusion. Carry out an activity to compare the rate of diffusion of two different gases. Apply Graham's law of diffusion in solving problems. Gas molecules are in a state of continuous and rapid motion. No force of attraction exists between the molecules in a gas. The volume of gases is negligible. The volume of a gas is given by specifying the volume of the vessel in which it is held. The average kinetic energy of gases depends on temperature. For example, in a hot air balloon, the air in the balloon is heated. The gas laws express the mathematical relationship between the volume, temperature, pressure, and quantity of a gas. Volume is the space taken up by a body. Remember, 1 liter is 1,000 milliliters, which is 1,000 cubic centimeters, which is 1 decimeter, cubic decimeter. Pressure is the force applied per unit area. The units of pressure are atmospheres, pascals, torrs, millimeter of mercury. This is often used in medical equipment. 1 atmosphere equals 760 millimeters of mercury, 76 centimeters of mercury, 101,325 pascals, or 101.325 kilopascal. The U shape on the bottom is the container. The T-shape, upside-down T-shape on the top is called a piston. When a piston is pushed down in a container, it creates pressure buildup inside of the container. The pressure force acts perpendicular to the enclosed surfaces. So pressure is force divided by the area. Temperature is the degree of heat of a body. The units of temperature are Fahrenheit, degrees Celsius, Kelvin, and Kelvin equals degrees Celsius plus 275. Celsius equals degrees in Fahrenheit minus 32 times 5/9. Alternatively, degrees Fahrenheit equals 9 divided by 5 times degrees Celsius plus 32. You may notice that the freezing point of water is 0 degrees Celsius, which is also 32 degrees Fahrenheit. Zero degrees Celsius is also 273.15 Kelvin. We do not say the word degree here. The standard temperature and pressure, or STP, is the conditions of a pressure where it has 1 atmosphere and a temperature of 0 degrees Celsius, which is also 273.14 Kelvin. At STP, the volume of 1 mole of any gas is equal to 22.4 liters, and this volume is known as molar volume. The quantity of gas is expressed in moles, or the lowercase n. A mole is the number of atoms or molecules in 1 gram atom or 1 gram molecule of an element or compound. Boyle's law states that the volume of a fixed mass of gas is inversely proportional to the pressure at constant temperature. So the volume is proportional to 1 over P. If this is at constant temperature and number of moles. The law is pressure 1 times volume 1 equals pressure 2 times volume 2. Pressure 1 and volume 1 represent the first condition. Pressure 2 and volume 2 represent the new or final conditions. So a piston pushing down into a cylinder creates pressure. And there is a new volume after the pressure is created. If the pressure increases, the volume of the gas decreases. The pressure in the third cylinder is greatest. For example, oxygen occupies 10 liters under a pressure of 790 millimeters of mercury. What will be the pressure required for oxygen to occupy a volume of 13 liters at constant temperature? The first volume is given, 10 liters. The first pressure is given, 790 millimeters of mercury. The second volume is given, 13.4 liters. We need the second pressure. We can plug in the numbers into Boyle's law and solve for P2. So we get 589.6 millimeters of mercury. Since the volume is lower, the pressure is lower. Said again, greater volume equals lower pressure, and smaller volume equals greater pressure. In this graphic, we can easily see the relationship between volume and pressure. Charles's law states that the volume of a given quantity of gas is directly proportional to Kelvin temperature at constant pressure. So V is proportional to temperature. This is at constant pressure and number of moles. In the first case, on the left, the sample is at a certain temperature and takes up a certain volume. When the temperatures increase, the volume increases. The variables here are temperature 1, volume 2, and temperature 2. For example, what is the new volume of a 2.5 liter sample of gas at a constant pressure if the temperature is changed from 500 Kelvin to 250 Kelvin? Volume 1 is 2.5 liters. Temperature 1 is 500 Kelvin. Temperature 2 is 250 Kelvin. We need to know volume 2. We know that volume 1 times volume 2 is equal to volume 2 times temperature 1. So volume 2 equals volume 1 times temperature 2 divided by temperature 1. So volume 2 is 1.5 liters. We can combine these two gas laws to express the relationship between pressure, temperature, and a volume of gas. Boyle's law and Charles's law are incorporated into one equation. P1 V1 divided by T1 equals P2 V2 divided by T2. Pressure 1, volume 1, and temperature 1 are the initial conditions. P2, V2, and T2 are the final conditions. A quantity of gas measures 206 milliliters at a temperature of 22 degrees Celsius and a pressure of 750 millimeters of mercury. What will be the volume under standard conditions, or standard temperature and pressure? We're given volume 1, pressure 1, and temperature 1. We have to change it into Kelvin. We're also given pressure 2 and temperature 2 because we know the standard temperature and pressure. We want to know the second volume. Using the given information, we will apply a combined gas formula to solve the problem. We can solve for V2, and V2 equals 188.1 milliliters. Avogadro's law states that equal volumes of all gases at the same temperature and pressure have the same number of molecules. Volume is proportional to the number of moles at constant pressure and temperature. The smaller the volume, the fewer moles. The larger the volume, the more moles there are. Keep in mind we are not applying any pressure or temperature in this example. An ideal gas is a hypothetical gas that obeys the gas laws. It is a combination of Boyle's law, Charles's law, and Avogadro's law, where R is the gas constant. So pressure times volume is equal to the number of moles times the gas constant times temperature. In these two situations, the ideal gas obeys the gas laws. They have a certain pressure, temperature, and volume, and number of moles. For example, if 150 milliliters of gas at standard temperature and pressure weighs 0.228 grams, what is its molecular weight? At standard temperature and pressure, pressure equals 1 atmosphere. Temperature equals 273 Kelvin. And the volume given is 0.15 liters. We know that it weighs 0.228 grams. And the gas constant needs to be looked up online or in a table, and it is in 0.082 liter atmospheres divided by Kelvin times moles. Remember to look up each gas constant with the correct units for your problem. we need to learn the molecular weight. So we apply the ideal gas equation. PV equals nRT, and N equals the mass divided by the molar mass. We know this from previous units. So let's solve for the molar mass. We get 34 grams per mole. We can check on the periodic table which gas this is. In Graham's law of diffusion, he studied the rate of diffusion of different gases. The law states that at constant temperature and pressure, the rate of diffusion of a gas, R, is inversely proportional to the square root of its density, D, or molar mass, capital M. Remember that this lowercase r here is not the gas constant. So the rate of A divided by the rate of B equals the square root of the diffusion of B divided by the diffusion of A, or RA divided by RB is equal to the square root of the molar mass of capital MB over capital MA. How many times faster is the rate of diffusion of phosphine than the rate of diffusion of ammonia? First, determine the molar mass of the gases. The first one is 34 grams per mole. The second one is 17 grams per mole. Then we can divide these two masses and take the square root. We just have a ratio of 1 divided by the square root of 2. So that's how many times faster the rate of one gas is than the other. In summary, Boyle's law is P1V1 equals P2V2. Charles's law is V1 over T1 equals V2 over T2. The combined gas law is P1 V1 divided by T1 equals P2 V2 divided by T2. The ideal gas equation is PV equals nRT. And Graham's law of diffusion is the ratio between the rates, the square root of the diffusion constants, or the square root of the molar mass ratio. Convert the following: 500 millimeters of mercury into atmosphere, torr, centimeters of mercury. For atmospheres, it is 0.657 atmospheres. For torr, it is the same as the millimeters of mercury. For centimeters of mercury, all you have to do is move the decimal place, so it's 50 centimeters of mercury. 100 cubic decimeters into milliliters, cubic centimeters, liters, and cubic meters. The answers are as follows. All in all, 100 cubic decimeters is equivalent to 100,000 milliliters, 100,000 cubic centimeters, 100 liters, 0.1 cubic meters. 54 Celsius into Kelvin and Fahrenheit. For Kelvin, we add 273 to get 327 Kelvin. For Fahrenheit, we have to multiply the degrees Celsius by 9 divided by 5 and add 32 to get 129.2 degrees Fahrenheit. A certain gas occupies a volume of 10 cubic meters at a pressure of 100 kilopascal. If its volume is increased to 20 cubic meters, what will be the new pressure of the gas assuming temperature remains constant? These are our givens, and P2 is what we need to find out. So all we have to do is apply Boyle's law and solve for P2 to get 50 kilopascal. At constant pressure, by what fraction of its volume will a quantity of gas change if the temperature changes from negative 173 Celsius to 27 degrees Celsius? Here are our given conditions. So we can use Charles's law. Starting at 17 degrees Celsius, at what temperature will the volume of gas be halved? We can use Charles's law. (145 Kelvin) or negative 128 Celsius. Doubled. We'll use Charles's law again. The answer is 580 Kelvin or 307 degrees Celsius. At 25 degrees Celsius and 1 atmosphere, a gas occupies a volume of 1.5 cubic decimeters. What volume will it occupy at 100 degrees Celsius and 1 atmosphere? Here are our givens and unknowns. We have to apply the combined gas law and solve for V2. The answer is 1.88 cubic decimeters. If a 50 cubic centimeter sample of gas exerts a pressure of 60 kilopascal at 35 degrees Celsius, what volume will it occupy at standard temperature and pressure? First, apply the combined gas law, then solve for V2. The answer is 26.24 cubic centimeters.